Okay, so this is problem 28 from chapter 6. The problem is if it requires 6.0 joules of work to stretch a particular spring by 2 centimeters from its equilibrium length, how much more work will be required to stretch it an additional 4 centimeters? So it may be worth drawing a picture, as always, and so let's kind of do that like this. Here's a spring, and there's a mass, call it M. And the spring has some constant K, and what's going to happen is, so this, let's call this 0, this might be the equilibrium position, and it's actually a spring that's going to start, so I'll kind of do a little dashed line here. The spring is going to start here at, so I have this wrong, it stretches from 0 to 2 centimeters in one go, and in that process, so from here to here, that requires 6.0 joules. And then the question is how much more work will be required to stretch it an additional 4 centimeters. So an additional 4 centimeters after the 2, which means extending this all the way to here, which would be at the 6 centimeter mark. So 6 centimeters away from equilibrium. A couple things that we might need. So we want basically this, we can call this the work done in the first case, and we want the work done in the second case. So what we are given is not too much information. We're given these distances, we're not given a mass, we're not given a spring constant. So let's see what we can do conceptually. Okay, we're in chapter 6, we've been talking about energy, so we should think about energy and conservation thereof. And usually this kind of simple problem, we assume that there's no friction or anything to worry about. So energy and conservation of energy is relevant. We're interested in moving something from rest to a different position to another position, and they're not telling us how fast. So we can assume it's moving very, very slow, or it moves and then it stops, and it moves and it stops. So we only have one kind of energy that we're interested in, that's potential energy, U, and specifically we're interested in spring potential energy, okay? We're interested in the amount of energy stored in the spring that's going to be related to how much work is required to stretch it out. There's a formula for that. So we've got our concepts and the formula that we might need. Formulae. Spring potential energy is given by 1/2 kx squared, where x is the distance from equilibrium, assuming that it's at 0. And also something to keep in mind is that when you do work on a system, that can change the system's energy. And since we only have one kind of energy to worry about, that's going to be the change in the spring potential. Okay, concepts, formula, or if you like, equations. Okay, so let's think about this. In the first case, let's just focus on the first part. Stretching from 0 to 2 centimeters, the work done is 6.0 joules. So we know that the 6.0 joules, that's the work done in the first case. It involves the change in the potential energy, ending at 2 centimeters, beginning at 0. So let me write this very explicitly. This is 1/2 kx final squared minus 1/2 kx initial squared. X initial is 0, so this whole term is 0. X final is 2 centimeters. We might as well write that in terms of meters so we don't get confused later on. I'm just going to go ahead and write that as 0.02 meters, and this is 0.06 meters. So that means that I can write this as 1/2 k 0.02 meters squared. Okay, so everything here is known except for k. We can solve for the spring constant, so that would be a good thing to do. Let's go ahead and do that. What you'll find is when you rearrange, you'll find that multiply by 2, divide by this. In fact, let's just do that real quick. Multiply by 2, that gives me 12.0 joules equal to k times, I like to do it like this. The 2.002, let's write that as 2 times 10 to the minus 2 meters and square that. Scientific notation can be quite useful. The 2 squared is 4. I'll divide that over. That would be 12 over 4 is 3. And then this becomes a 10 to the minus 4, dividing by 10 to the minus 4 overall. That would give me 3 times 10 to the 4. Let me check that that's right. That's what I have over here. I've got joules. I'm dividing by meters squared. And apparently that's what K is. Does that make sense, though? I thought that K had to have units of force per distance. So let's just look at this closer. Joule, that's the same as a Newton per meter. And we divide that by a meter squared. In fact, it is a Newton per meter, so we know that that is K. That's an answer that we're going to need now to do the second part, the work in the second case to stretch it out. So that work, it involves the change in the potential energy, final minus initial. In the end, it ends up at the final position of 6 centimeters, 0.06 meters squared, minus 1/2 K, 0.02 meters squared. It's very tempting to just kind of look at the going from 2 to 6 and think, oh, well, that's a distance of 4 compared to a distance of 2. It should be just double. Because the potential energy depends on the square of the distance, it doesn't grow linearly. When we plug in our value for K into this formula, what you should find is that this is approximately, or exactly, equal to 48 joules. And that is your final answer.